So whenever you chat with an LLM, you type in words, right? But the model itself, it doesn't see words, it sees numbers. And the magic that happens in between is called tokenization. It's truly the unsung engine of modern AI. It's this absolutely critical bridge between our human language and the machine's world of computation. And its evolution, well, it's a fascinating story of brilliant solutions to some really tough problems.
Here's the journey we're going to take. We'll start with what researchers called the vocabulary crisis. Then we'll look at the first big breakthrough, BPE. After that, we'll see how things got even smarter with probabilistic models and something called subword regularization. And finally, we'll land on the modern tools that AI developers are using right now.
All right, let's rewind the clock to the mid-2010s. Neural machine translation, or NMT, was taking the world by storm. It was amazing, but it had this one massive, glaring flaw that was holding everything back.
Check out this German word, ja, Abwasserbehandlungsanlage. It means sewage water treatment plant. And for an early NMT model, this word was an absolute catastrophe. See, languages like German love to glue words together to make new ones. This means you have a basically infinite number of possible words, and there's just no way a model could learn them all during training.
This was the heart of what's known as the open vocabulary problem. The models had a fixed dictionary, maybe 30,000 to 50,000 words. If it saw a word that wasn't in its dictionary, it became an out-of-vocabulary token, or OOV. The model had no idea what to do with it. Translation would just break. And this wasn't just a German thing. It happened with rare words, with names, with slang, in every single language.
So where did the solution come from? You might think it came from linguistics, right? Nope. The answer came from a totally different field, data compression. Researchers found their inspiration in an algorithm that was already decades old.
In 2016, a paper by Sendrick and his colleagues changed everything. They took a compression algorithm from 1994 called Byte-Pair Encoding, or BPE, and did something brilliant with it. Their big idea was to stop treating words as the smallest, most basic unit of language. Instead, they decided to break them down into smaller, frequently used pieces, or subwords. So how does BPE actually work? Well, it's a pretty simple, iterative process. You start with a vocabulary of just individual characters. Then you scan your text and find the pair of characters that appears together most often, in this case E and S. You merge them to create a new subword, S, and add that to your vocabulary. Then you just repeat that process over and over, always merging the most frequent adjacent pair.
And the results? They were fantastic. On a standard translation benchmark, the BPE subword model scored a higher BLEU score, that's a measure of translation quality, than the old models. Now, a half-point gain might not sound like a huge leap, but in the world of machine translation, that's a really solid win. It proved that subwords were the way to go.
So BPE was a game changer. Problem solved, right? Well, not quite. BPE was deterministic, meaning for any given word, it would always chop it up in the exact same way. But that led to a deeper question. Is there always just one correct way to segment a word?
It turns out the answer is no. Groundbreaking work from Taku Kudo in 2018 showed that segmentation is actually really ambiguous. I mean, just look at this. The simple phrase, hello world, can be broken down in multiple perfectly valid ways, and each one gives the model a totally different sequence of numbers. BPE's one-size-fits-all approach was missing this nuance. And this insight led to the Unigram language model, or ULM. It kind of flips BPE on its head. Instead of starting with characters and merging them up, ULM starts with a huge vocabulary and works its way down, pruning the least useful pieces. The key difference is that it's all based on probability. It doesn't just give you one answer, it can give you many possible segmentations, each with a likelihood score.
Okay, so now we have a tokenizer that can give us multiple ways to segment a word. And this is where things get really, really cool. What if that ambiguity, that uncertainty, wasn't a problem to be solved, but a feature to be used?
This is the core idea behind a technique called subword regularization. During training, you don't just feed the model the same tokenized sentence every time. Instead, you randomly sample from all the different possible tokenizations. It's a form of data augmentation that makes the model way more robust, forcing it to learn that different combinations of subwords can mean the same thing.
So, in practice, here's how it works. For every sentence that goes into the training pipeline, the Unigram model spits out a bunch of different ways to slice it up. We randomly pick one for that specific training step.
The next time the model sees that exact same sentence, it will almost certainly be training on a different segmentation. It keeps the model on its toes.
In the payoff, it was huge. Especially when you look at how the model performs on out-of-domain text, basically text that's really different from what it was trained on. A standard BPE model scored around 22.7, but the same model trained with subword regularization jumped all the way to 26. That's a massive improvement in the model's ability to generalize and handle the messy, unpredictable language of the real world.
And all of that brings us right up to today. All of this incredible research, all of these clever ideas are now packaged into the modern tools that researchers and developers use to turn our text into tensors that a model can understand.
When you look at the timeline, you can see this beautiful, clear progression of ideas. It all starts with the data compression algorithm back in 1994. It gets adapted for NMT in 2016. Then it's refined with probabilistic methods in 2018. And now that entire history is embedded in the software we use every day.
Two of the biggest players today are Google's SentencePiece and Hugging Face's Tokenizers library. They are incredibly fast and efficient. Their job is to handle that final, critical step of turning raw text into the perfectly formatted tensors the model needs, things like input IDs and attention masks. And really, it all boils down to this single line of code. Decades of research, the vocabulary crisis, compression algorithms, probabilistic models, regularization, all of it just distilled right into this one simple, incredibly powerful command. So it feels like we've kind of solved tokenization. But you have to wonder, what's next? We've gone from whole words to these algorithmically derived subwords. Is the next step for models to learn their own subatomic units of meaning directly from the data without any of our human-designed algorithms at all? It's a fascinating question.
And that's a wrap on our deep dive into the powerful engine that makes modern AI possible. Thanks so much for joining me. This has been The Explainer, brought to you by ByteGoose AI.